Hi, welcome to Integrated Science. We are in the space unit. So far, we've talked about scale models and our solar system and the distances that we can measure in space using kilometers and astronomical units, light years. We've gone through and we've talked about the orbits of our planets that are held together by gravity, and that big luminous object in our sky that holds it all together because it's the most massive, the sun. That's what we're going to talk about today, and its important parts and functions. It actually has several different layers that we're going to discuss today, and then we're going to rehash some of our thermodynamic terms that we've talked about previously with conduction, convection, and radiation. And then we'll also talk a little bit about the Parker Solar Probe, which is a satellite that is the closest that any object has ever gotten to the sun, that is recording all kinds of data for us to have and look at back here on Earth. So without further ado, we're going to talk about the sun today. So in Canvas, you're going to want to pop on down to the space unit, and in there should be some notes talking about sun, earth, and moon. We're mostly going to talk about the sun today. I will pop back and talk about the moon a little bit, just a little bit later, but mostly today just the sun. So when you pull that PowerPoint up, it should look something like this. And so let's go ahead and kind of chit chat just what about this the sun looks like a little bit. So first off, a lot of times students don't even realize that the sun is a star, and so scientists are able and astronomers are able to look at stars and figure out many different things about them. We can figure out how old they are, we can figure out how hot they are, we can figure out even how much elements they have within them. Most stars start out with, well, not most, all stars start out with mostly hydrogen, and then they fuse together helium, and we'll talk a lot about that today. But the sun in general, that you can kind of see that it's gone through here, and we are talking about some of the different layers of the sun today. So it does have a core. It has a zone called the radiative, the convection zone, the chromosphere, photosphere, and then these other cells too. So we're going to break that down just a little bit. The sun, though, is obviously a star. It's the closest one in our solar system. It's an average size star, so it's a medium size yellow star. That's normally what it will be referred to as we move forward in this class. So there are stars that are way bigger, and there are stars that are even smaller. So it's kind of like the middle of the road type star. And Earth is just luckily just the perfect distance from where we have liquid water. And so we'll even talk about that too. We're in what we call the Goldilocks zone, which is a good zone to be in, obviously. So first off, let's revisit radiation just a little bit. So remember our three types of thermodynamics. We had conduction, convection, and radiation. So radiation is that process of energy moving through waves. And we did a whole big section about waves and talked about frequency and wavelength and wave speed. So radiation is kind of moving back into that. So a photon is a bundle of energy that is moving light. So if you think about, we talk about matter being a solid, liquid, or gas, it has protons, neutrons, and electrons, our subatomic particles. Light does not have that. Remember, it's just energy that is being disruptive through a magnetic and electrical fields. So a photon is a representation of that for us, and that's what we're going to talk about, these photons, these bundles of energy. So a photon is a particle of light or radiation. If I were to give you a photon, you would not be able to measure it with mass. Once again, they are just a frequency of energy, and that's what this is saying down here. A photon carries energy proportional to the radiation frequency, but has a zero rest mass, meaning that there's no mass. You cannot measure how much a photon weighs, but it has that energy, that frequency. And so remember, if we talked about if it's a photon that has a high frequency, we're looking at very short wavelengths, and if we are talking about a photon that has low energy, we're talking about very long wavelengths. So sun's layers, there's several of them that we're going to kind of go through, and I'm going to start from the outermost layer and work my way in. So I'm kind of talking about the atmosphere of the sun, if you want to think about it with these three layers. The first one is the corona, poorly named at the time, which is the outermost layer. And so this is a layer that actually, if you were to look up at the sun, which I do not recommend that you do for long periods of time, it will hurt your eyes. It will burn your corneas, and you definitely don't want that. That happened to Galileo. He actually went blind, one of the good gentlemen that we talked about, who kind of developed the telescope. So the corona is the outermost layer. It's actually very dim. That's why we don't normally see it. The only time that we can see it is when we have a solar eclipse, and that's when the moon moves in front of the sun, and we can see that outermost wispiest layer. That is the corona. Below it, and we're going to spend some time talking about this one very much, is the chromosphere. And this is a layer where sunspots are formed, meaning that sunspots are almost like blemishes on the sun. And this is where our magnetic fields are generated for the sun. And we can tell by how many sunspots what type of cycle the sun is going through. It will go through two different types of cycles, which is called solar maximum and solar minimum. Currently in 2020, we are going through a solar minimum, meaning that the sun isn't extremely active. It still has a lot of energy and everything, so I don't want you to think that way. It just is not as violent as it could be, which is an okay thing. So normally when that happens in the chromosphere, we do not see as many sunspots. So if you were able to look at the sun through a telescope, which we do have ways to do that. They have like little almost sunglass caps that we can put on telescopes, and we can see these sunspots. I'll show you some pictures here in a little bit. And then the final layer in the sun's atmosphere is called the photosphere. And this is a layer that we see every day. So if you were to look up in the sun, we actually can't see the blemishes of the sunspots on it, nor do we see the corona. We only see that photosphere, and that's the layers that we see. And then inside that, we have the inner layers of the sun. And two of those terms should sound really, really, really familiar. The first one is the convection zone. And this is where photons are going to spend a long, long time in. So once again, remember with our scale models, the sun is really, really big. And so photons can spend about 170 million years in the convection zone. And once again, that's just heating up, cooling down, heating up, cooling down. And that heating up, cooling down process creates those sunspots in the chromosphere. So they kind of are connected ever so slightly. That convection is radiating up that heat to generate out into space. So very long cycle though, but remember our convection cycle is warm liquids and our gases that are heating up, and that warm gas heats up, it rises, it cools, it sinks back down. Warms up, rises, cools, sinks back down. And so this is happening in that zone. So it's a very active zone. Below the convection zone, that's where it's heating up those gases, is the radiative zone. And once again, it's just energy that is moving through the core, which is the most important part of a star. It's what keeps a star being a star. And so in order for a star to be called a star on the main sequence, and we'll talk about this. Main sequence just mean that all stars are doing the same thing, which is just this. So it says gravity is so strong here that it brings hydrogen together to initiate fusion. So there's hydrogen particles all bouncing around in the core, and it's so gravitationally strong that they bounce into each other. And when you get 4 of the hydrogen atoms bouncing into each other, they will fuse together and then form helium. And so this fusion is the process that is important. It's a stage in which a star is actually on the main sequence, and it's doing what all the other billions of stars are doing in the night sky, is that it's burning hydrogen into helium. And then we'll talk about the different stages and what could happen as we kind of move through the different masses of stars. So once again, just kind of the harp on fusion. This is a really important part. So fusion is when hydrogen burns or fuses together to form helium. And you need, once again, 4 hydrogen. You can kind of see this from the picture here. 4 hydrogen molecules that are forced together. They're pushed together and fuse and then become a helium atom. And that is what we call fusion or nuclear fusion. And so with that, we also have a term called hydrostatic equilibrium, which just means that it's staying static. It's staying the same. So remember, we've talked about equilibrium before, and this is now happening in stars. And it just says gravity and pressure on all sides push against each other, keeping the sun from flying apart, meaning that in the core of a star, it's almost like huge nuclear explosions going off. So it's one thing to push outward and outward and outward, but gravity is pushing inwards from the outside because it's spinning as well. So remember, we talked about that accretion part of the nebula theory. This is kind of that idea, is that gravity is pushing on all corners of the star, pushing it inwards, and this fusion is pushing outwards. And as it does that, it keeps it balanced, so it stays in a nice spherical shape. Magnetic fields. So we talked about magnets way back a couple weeks ago, where we have an electrical current that can create a magnetic field. So the sun is also doing this. It's electrically charged particles that are being moved. The sun is made out of a state of matter which is called plasma, which is kind of not an in-between a gas and a liquid, but the plasma moves kind of like both, but it's electrically charged particles, and as it does that, it creates a magnetic field too. So once again, these magnetic fields are created by the sunspots, and so it says the structure of the sun's corona is shaped by the magnetic field. So when we look at the corona, you can see almost wispies coming off the sides, and the sun's magnetic field can be extremely strong depending on where it's connecting. And so magnetic fields can be thought of as lines that connect both the north and south polarities. And so it's going to connect with one sunspot to the next, and it makes all these little loops that kind of jet out, kind of what you would think on Earth. However, the sun is much bigger, so it has many more sun spots, which then it can have many more pole areas too. So it has lots and lots and lots of magnetic fields, and it can kind of get all tangled up, almost like a yarn ball, is that they can be moving every which way. So energy moves through the layers of the stars. So once again, just kind of revisiting. So convection, hot gas moves upwards, away from the star center, cools and sinks, and then our radiation is of atoms absorbing energy and transfer it to other atoms in random directions. So that radiation zone is much closer to the core, and then it is heating up the convection, causing those particles, those photons, to move through. So how we know this is that we observe the sun through many different forms of radiation. So, and that's what this is saying here. Stars produce a full range of electromagnetic radiation, from high energy X-rays to low radio waves. So we can put like almost filters through different types of satellites to view what the sun looks like when it is emitting radio waves, which it does it all the time. We can just filter out everything else and just see the red radio waves. Or we can filter in then the blue and look at X-rays. So it's emitting all these different energies. Some are stronger than others. Our sun is not super exposed with X-rays. It's not like you walk outside and be like, oh my gosh, I'm gonna have to wear a lead suit today because I don't want to be exposed to too much X-ray. That's not the case, but UV definitely. And the last thing I want to talk about here is stars' temperature. So hot objects glow with white, that a short wavelength, and cool objects glow with a light of a longer wavelength. So in space, it's kind of reversed to what you're thinking about. Things that are really, really hot are almost bluish to white, whereas things that are cooler are more on the red side of the spectrum. So our sun, once again, we normally say is a yellow medium star. So it's kind of on the cooler end of the spectrum. It's not as hot as some other stars will be. I am going to spend some time. I wanted you to kind of see this here. It's Parker's Solo Probe.